So I'm going to be presenting black box variational inference. This is joint work with Sean Garish and Dave Bly. So in latent variable models, you try to model dependencies between some hidden state and your observations. These dependencies can range anything from network-style dependencies, factor-based dependencies, or time-based dependencies. Given your latent variable model and your data, the problem you want to do is to approximate the posterior distribution. That is, approximate the probability of the latent states given your observations. And this can be challenging. Let's look at a simple example. So in this example, we are looking at 3 steps of a time series. Here in the bottom, the L's are shaded. They're the observations. They're lab values measured at a visit to the doctor. So you can think about like cholesterol, blood pressure, things like that. The X's are the latent states that represent the state of the patient that travels through time. And doctors would like these latent states to represent amounts, so we make them positive. And once you make them positive, we chain them by expectation. That is, the expectation at the current visit is equal to the value at the previous visit, sort of like you see in a Kalman filter. And that's what that gamma E means, the expectation variance parameterization of the gamma distribution. But once you do that, inference becomes difficult. So standard variational inference and Gibbs sampling don't really work, namely because the complete conditionals aren't nice to play with. That is the probability of a latent variable given everything else. Our approach here is based on variational inference. It's much faster than doing Gibbs sampling where each complete conditional is sampled by a Metropolis Hastings. It allows us to try many models. Let's review variational inference. So what variational inference says is we want to do the posterior computation as an optimization problem. Specifically, we want to choose a member of a family Q that minimizes the KL divergence from Q to P. If we look at this a little bit more carefully, we see that X are the observations, our lab values. Z are latent variables, like the patient states. We have some sort of modeling distribution, and we have some sort of approximating variational family Q. So minimizing the KL divergence can be seen as maximizing this thing called the evidence lower bound, and that's how you get a variational inference algorithm. So how do we derive these things generally? So first, notice that the parameter of our variational objective is this lambda. Now on the right-hand side, this lambda appears implicitly through the distribution of Z. So the first thing we need to do is compute this expectation. And computing this expectation, even if it has closed form, is a pain. There's an old joke that goes that by the time you finish deriving your variational inference algorithm, your sampling algorithm is done running. But even then, when you have the expectation, you can't actually compute it in closed form. A simple example of this is in Bayesian logistic regression, where I have a normal approximating family. Then that term right there appears, and it doesn't have a nice mathematical form. So how do we get around this? Well, we use black box variational inference. So what are our goals with black box variational inference? We want to easily use variational inference. We don't want to sit down and compute all these annoying expectations. And basically, we want to minimize the mathematical work necessary. Let's try to look at this pictorially. So basically, our goal is the following. So we want a set of variational families that we can reuse. We want a model that goes in. We want a data set that comes in. And we want some sort of approximate posterior to come out. And this seems a little like magic at first, but the way we avoid computing these expectations and gradients is by using noisy gradients of the ELBO. So to maximize a function using noisy gradients, we use stochastic optimization. Specifically for a function f, if you have a unbiased gradient, h, so h is a random variable, which in expectation is a true gradient. If you step in the direction of that noisy gradient according to these step size conditions, you'll converge to a local optimum. The first condition sort of means if you're far enough away, you'll get there. The second condition is control the noise. So how do we get a noisy gradient of the ELBO? So the ELBO is written as an expectation. With a little bit of algebra and moving some derivatives and expectations around, you can also write the derivative of the ELBO as an expectation. And this is really cool, because once the derivative of the ELBO is an expectation, we can get unbiased gradients really simply by Monte Carlo. That is, we draw a couple samples from the variational distribution, and we evaluate that function on the inside. So what do we need to compute the noisy gradient of the ELBO? First, we need to sample from the variational distribution. Then we need the derivative of the variational, or the log of the variational distribution with respect to its parameters, the score function. And we need to be able to evaluate both the log p and log q. So what does this mean practically? Well, defining log p is the same as defining the model. Like our graphical model is just the log joint distribution. And there are a bunch of computations about q that we need, but they can really be shared across models. For example, in Bayesian logistic regression, you have a normal approximation, and in probabilistic matrix factorization, you can use a normal approximation, and that the computations you need are the same for both of them. So let's look at an algorithm putting this all together. So let's go through this. And the first thing we do is we sample from our variational distribution, Q. We draw as samples. We get a step size. We construct our Monte Carlo gradient. Then we just step in that direction. It looks pretty simple, and theoretically, this is guaranteed to converge to a local optima. But unfortunately, the variance of the estimator can be very high. And we address this in two ways. First, we address this with Rao-Blackwellization. Rao-Blackwellization basically says if you're trying to estimate the expectation of a function of two random variables, say with Monte Carlo, you want to take the conditional expectation with respect to one of them, and you get a lower variance estimate. At this point, you should probably be yelling at me a little bit, because I spent the previous few slides saying don't compute expectations, don't compute gradients, but now I'm saying compute a conditional expectation. But if done appropriately, taking advantage of the structure of the joint distribution and the variational approximation, you can Rao-Blackwellize with respect to the Markov blanket. It's a little technical, and feel free to come to the poster to see how it's done. But the thing to take away from this is that our algorithm is still a black box in that there are no real computations about log p needed to get the gradient. Log pi here means we're looking at the terms in the joint that have the variable zi in them, sort of the Markov blanket. The second way we reduce variance is with control variates. So control variates, so if we want to estimate the expectation of f with Monte Carlo, we replace it with the function f hat. And from this, we can see that f hat has the same expectation no matter what the choice of a or h are. H is some function we can choose, and a we set to minimize the variance of f hat, which can be computed analytically. So how do we choose a good h? Well, one, you can see that good h have high correlation with f. The way to see this is if you plug in f for h, you'll get a 0 variance estimator. But that isn't really helpful, because if we plug in f, you see that we need to know what the expectation of f is on the right. So instead, we use something very, very simple, going along the analogy of black box variational inference. That is, we use the score function, which has expectation 0 for any q. It's pretty easy to use. So do these really help us? So on top, we have our basic estimator, which is the very first one I showed. And the second one's the Rao-Blackwellized one, and the last one's with control variates. On the y-axis is on log scale, so we can see that the variance is reduced by several orders of magnitude. And in fact, even when we ran the basic algorithm in the time allotted, it didn't make much progress. So I'm going to go over a couple of extensions. First is fairly straightforward. We don't want to change the hard, well-defined problem of computing expectations to the soft problem of dealing with step sizes, especially because probability distributions can have different parameterizations, so learning rates can be a real nuisance. But we found in practice that Addergrad works pretty well, which is a per component learning rate that scales for both the length scale and the variance of each component. And we also have to compute the entire likelihood of our model for all our data points. And that's kind of a nuisance, because if you have a lot of data, that can be really slow. And so we address that by subsampling observations. Specifically, in a hierarchical Bayesian model, the joint distribution of the model factorizes in a nice form. So if we have global latent variables beta, local latent variables z1 through n, the log joint distribution splits into that term. And now once everybody sees the sum on the right, they'll be like, to get a Monte Carlo estimate of this, all I need to do is sample uniformly and scale by n. And that can provide a huge computational speedup for us. And this generalizes the stochastic variational inference algorithm of Hoffman et al., which only works in this specific modeling setting called the conditionally conjugate exponential family. So let's go back to our model. We would like to fit this model. If you recall, we have this time series. They're chained by positive values. We have lab values as observations, and we generate them through weights. Let's look at that a little bit more carefully. So specifically, we have this weight matrix that converts between the patient factors and the lab values. We draw offsets, which are like, how is each patient when they come to the doctor? And then we draw their initial health state. And from that, we run this time series that says, given your health state, your next health state and expectation is your previous one, and then the labs are an observation. The labs are generated from the weights in your health state. It's basically a small modification of the Kalman filter. But more interestingly, black box variational inference can fit this much, much faster than Gibbs sampling could. We let both algorithms run for 20 hours. And in the time that we ran, Gibbs sampling was still improving, but it never reached a predictive likelihood, higher is better, that black box variational inference reached. You can also notice something else, that there's this small downward slope, that if you run the variational inference algorithm for a long time, you do see some sort of overfitting. We were also able to test out several different models. So our framework just requires the log joint. So we tried out different models, breaking the time series. So gamma normal TS is what we just saw, where we have positive factors, we have real valued weight matrix, and we have a time series. And the ones without TS don't have time, and the gamma-gamma models are models where the weight matrix is positive. From this, we can see that time helps us, and that sort of makes sense. How healthy you were yesterday is related to how healthy you are today. And the other thing we see is that the gamma-gamma models don't really do that well. And this is really because they're bad models in that they can't capture negative relationship between the lab values. But the key takeaway from this is that without black box variational inference, you'd have to sit down and come up with your own approximations, do a Laplace approximation or Taylor approximation to get this to work. Changing gears a little bit, I'm going to talk about a recent application of black box variational inference to fMRI data. The thing we see on the left there is a big fMRI machine. So in that, you sit down, you're laying down, you're looking at a particular stimuli while your head is in that big magnet, and it measures the blood flow at different locations of your brain under a particular image or video that you're looking at. What neuroscientists would do is they would like to see what parts of your brain are activating and how they're related. So given that data, they'd like to come up with something on the right, where the little black things are portions of your brain, like parts of your brain that are interesting, and the connections are either positive or negative weights between those sources. So they came up with this model called topographic factor analysis, which is a factor analysis, but in the spatial sense, where here we have k components. They have some parameters. In this case, it's the center and width of a radial basis function. And those images are generated by a linear combination of the weights through the radial basis function. That nonlinearity makes inference in this model difficult, especially if you want to tweak around what that function is. You'll need a new approximation every time. But with black box variational inference, we were able to actually recover that network that we saw on the previous slide. And on the left, you see the original data that an fMRI machine would produce. In the middle, you see what the reconstruction is given by topographic factor analysis. On the right is the interaction between the sources for a particular stimulus. And even cooler is you can ask the question, how does your brain vary based on different stimuli you see to see how your brain interacts? And on the left, we have animals, we have insects, then tools and vehicles. It's kind of weird that vehicles and animals look similar. But I think the key takeaway here is that black box variational inference allowed us to get these networks and help provide some insight for the neuroscientist. So in summary, for black box variational inference, what we need is the log joint of the model and some computations about the variational approximation that can be shared across several models. Thanks.
The overfitting that you saw, do you think that's because of the step size discrepancy, or?
So the variational objective is still increasing. So I think that would have to do with the problem with variational inference itself.
I see.
Yeah.
So in the neuroimaging example, were you doing reverse and predictive inference?
Reverse, I'm not sure what that is. You'll have to,
Okay,
we can talk
sorry.
about
So
that.
just in the neuro example, did you do any type of comparison to other methods to see how you were being able to break up, for example, the structure of like animals, insects, and tools to see how it was doing predictive power against other types of models like ridge regression or
So I mean,
elastic net or something like that?
yeah, so it was simply compared against regression itself, and the predictive power is worse than if you're using every single voxel. But the goal was to really provide a semantic representation more than just predictive power, because having those really tight parameterization and sources in the brain help neuroscientists understand what's going on, rather than having sort of disjoint weights over voxels.